12th, and the subtopic is as follows. Okay, the next subtopic is for the class 12th is combination of the thin lenses in contact. Okay, you will see. Consider two lenses A and B, and this is the lens, convex lens. Which type of lens? Convex lens. A and B of focal length f1 and f2. Focal length f1 and f2. In this figure, we are talking about in this figure. Okay, the next one is f1 and f2 placed in contact with each other. Let the object be placed at a point O beyond the focus of the first lens. Okay, first lens we are talking about in this figure. Hi everyone. The first lens produces an image at I1. Since image I1 is real, it serves as a virtual object for the second lens B, producing the final object image at I. It must, however, be borne in mind that the formation of image with the first lens is presumed only to facilitate determination of the position of the final image. In fact, the direction of the ray emerging from the first lens gets modified in accordance with the angle at which they strike the second lens. Hence, since the lens are thin, we assume the optical center of the lens to be coincident. Let this central point be denoted by P. In this, we are talking about in this figure. Okay. Yeah, and it is called as principal. Okay. For the image formation by the first lens, we have to take the formula 1 upon V1 minus 1 upon U equal to 1 upon F1. For the image formation of the second lens B, 1 upon V minus 1 upon V1 equal to 1 upon F2. So adding equation 1 and 2, we have to add this both equation 1 upon V minus 1 upon A equal to 1 upon F1 plus 1 upon F2. If two lenses system is regarded as equivalent to a single lens of focal length f, where hello everyone. Now 1 upon V minus 1 upon U is equal to 1 upon F, so that we get 1 upon F is equal to 1 upon F1 plus 1 upon F2. So the deviation is valid for any number of thin lenses is contact. If several thin lenses of focal length f1, f2, f3 are in the contact, the effective focal length of their combination is given by 1 upon f equal to 1 upon f1 plus 1 upon f2 plus 1 upon f3 and plus so on, plus so on. It in terms of power, okay, it can be written as P is equal to P1 plus P2 plus P3 and plus so on. Okay, it will go on so on, where P is the net power of the lens combination. Note that the sum in equation 9.32 and in this equation, okay, is an algebraic sum of the individual powers. Okay, so some of the terms on the right side may be positive for convex lenses, and the some negative. Okay, some negative for concave lens. Combination of the lenses helps to the obtain diverging or converging lenses of the desired magnification. Okay. It, it also enhances sharpness of the image, since the image formed by the first lens becomes the object for the second equation implies that the total magnification m of the combination is a product of magnification m1, m2, m3 and so on individual lenses. Okay, so m is equal to m1, m2, m3 and so on. Such a system of a combination of the lens is commonly used in the designing lenses for cameras, microscope, telescope and other optical instrument. Okay, the next subtopic is refraction through a prism. Refraction through a prism, and this is the prism we will talk about in this figure. Okay, so in the passage of the light through a triangular prism ABC. Okay, the angle of the incidence and the refraction of the first face AB are I and R1, while the angle of the incidence from glass to air at the second face AC is R2, and the angle of the refraction or emergence E. The angle between the emergent ray RS and the direction of the incident ray PQ. In this figure, we are talking about this. I am talking about totally in this figure. Okay, it's called the angle of the deviation, delta. What is called delta? Okay, in quadrilateral A Q N R. Okay, in this figure AQNR. Okay, so in a quadrilateral AQNR of two of the angles at the vertices Q and R right angles. Therefore, the sum of the other angle of the quadrilateral is 180 degree. You know that angle A plus angle Q and R is equal to 180 degree from the triangle AQNR. QNR in this we are talking about in this figure. Okay. So R1 plus R2 plus angle Q and R is equal to 180 degree. Comparing these two equations, we get R1 plus R2 is equal to angle A. The total deviation delta is the sum of the deviation at the two faces. Delta is equal to I minus R1 plus E minus R2. That is delta is equal to I plus E minus A. Thus, and this is also equation. Okay, and this is also the equation. Okay. Thus, the angle of the deviation depends on the angle of the incidence. A plot between the angle of the deviation and the angle of the incidence is shown in figure 9.22 in the next pages. Sorry, on the next pages. And here we can see the any given value of delta except for I is equal to E, I is equal to E correspond to the values I and hence of E. This, in fact, is expected from the summary of I and E in equation 9.35 in this equation. Okay, delta remains the same of I R. E is interchanged, and this is the figure. Okay, now we will talk about this figure. Physically, this is related to the fact that the path of the ray in figure 9.1 in the last figure can be traced back, resulting in the same angle of the deviation at the minimum deviation dm. Minimum deviation dm, the reflected ray inside the prism becomes parallel to its base. Okay, we have delta is equal to dm, I is equal to e, which implies r1 is equal to r2 is equal to r2 in equation 9.3. 3, 4. We have seen last pages, on the last pages. 2r is equal to a, or r is equal to a upon 2. Okay, in the same way, dm is equal to 2i minus a, or I is equal to a plus dm upon 2. The refracting index of the prism is n21. N21 is equal to n2 upon n1 into sine in bracket a plus dm upon 2 upon sine a plus 2. Okay, this is also the formula. Now the next one is angle a and angle dm. Okay, angle a and angle dm can be measured experimentally. Equation 3 point, 9.38 in this equation. Okay, this provide a method of determining refractive index of the material of the prism. For a small angle prism, a thin prism, dm is also very small, and we get n21 is equal to sine a plus dm upon 2 upon sine a upon 2 will equal to, see, sine will cancel, so a upon 2, a plus dm upon 2 upon a upon 2. So again 2 and 2 cancel, and it will come dm is equal to n21 minus 1 into a. Okay, this is the also a formula. It implies that a thin prism do not deviate light much. Are you getting? If you are getting, so please like and subscribe. So next one is optical instrument. We will talk about the subtopic optical instrument, and this one is a number of optical devices and instruments have been designed utilizing reflecting and refracting properties of mirrors, lenses and prism, lenses and prism, periscope, kaleidoscope, binocular telescope. Okay, microscopes are some example of optical devices, instruments that are in the common use our eyes. Of course, one of the most important optical devices that the nature has evolved with us. Okay, we have already studied about the human eye in class 10. We now go on to describe the principle of the working of the microscope and telescope. Okay, the next subtopic is the microscope. So hold on a few seconds. I'm coming. Okay, welcome back. The microscope. A simple magnification of the microscope is a converging lens of a small focal length. Okay, a small focal length in figure 9.23, and we will talk these all figures 1, 2, and 3. Okay, these are the figures we will talk similarly. So next one is one focal length, such a one focal length or less, focal length away or less, and the eye is positioned close to the lens on the other side. The idea is to get an erect, magnified, and virtual image of the object at a distance so that it can be viewed comfortably, sorry, comfortably at 25 centimeter or more. If the object is at a distance f, the image is at infinity. However, if the object is at a distance slightly less the focal length of the lens, the image is virtual and closer than infinity. Although the lens comfortable distance for viewing the image is when it is at the near point distance 25 centimeter approx. It causes the some certain some strain on on eye. Okay, therefore, the image formed at infinity is often considered most suitable for viewing by the relaxed eye. We saw the both cases first in figure 9.23 and another A and B. See, A and B, and second one figure B and C, B and C. Okay, the linear magnification M for the image formed at the near point D by a simple microscope can be obtained by using the relation. Okay, the next one, magnification equal to V by U, and we have to put the value V is equal to V into bracket 1 upon V minus 1 upon F equal to 1 minus V upon F. Now, according to our sign conventions, V is negative and is equal in magnitude to D. Thus, the magnification is M is equal to 1 plus D upon F. Okay, this is also a formula. Since D is about 25 centimeter to have the magnification of 6, so one needs a convex lens of the focal length F is equal to 5 centimeter. Note that M is equal to H dash upon H, where H is the size of the object and H dash is the size of the image. This is also the ratio of the angle subtended by the image, okay, to that the subtended by the object. If placed at D for the comfortable viewing, note that this is not the angle actually subtended by the subject at the eye, which is H upon U. What is the what is single lens simple magnifier achieves at this at that it allows the object to be brought closer to the eye than D. Now we can see we will now find the magnification when the image is at infinity. In this case, we will have to obtain the angular magnification. Suppose the object has a height h, maximum angle it can subtended can be clearly visible without a lens is when it is at the near point. Okay, distance d, the angle subtended is to the given by tan theta 0 equal to h upon d is similar to theta 0. Now find the angle subtended at the eye by the image when the object at u from the relation h upon h dash upon h is into m equal to v by u. We have angle subtended by the image tan theta I equal to minus h upon minus v equal to h upon minus u multiply h upon v upon u. We cancel, so h upon minus u equal to theta. Angle subtended by the object when it is at u is equal to minus f. Okay, theta 1 is equal to h upon f. It is clear from the angular magnification is therefore m is equal to theta I upon theta 0 equal to d upon f. This is also a formula. Okay. Okay. The next we will continue. This is one less the magnification when the image is at the near point, but the viewing of more comfortable and the difference in magnification is usually small. In in subsequent in subsequent discussion of the optical instrument, microscope and telescope, we shall assume that image to be at infinity. Okay, and this is the figure. Now we will talk. about this figure. A simple microscope has a limited maximum magnification less than or greater 9 for realistic focal length. For much larger magnifications, one uses two lenses can compounding the effect of the other. This is known as the compound microscope. A schematic diagram for a compound microscope is shown in figure 9.14 in this 24. This is the figure. A lens nearest the object called the objective from forms a real inverted magnified image, image of the object. This serves as the object for microscope or magnifier produces in the final image, which is enlarged or virtual. The first inverted image is thus near at within the focal plane of the eyepiece at a distance appropriate for final image formation. Okay, at infinity, at a little close to the image formation at the near point. Clearly, the final image is inverted with respect to the original object. Original object. We now obtain the magnification due to the compound microscope, the ray diagram of in this figure, so that the linear magnification due to the object, namely h dash upon h, equals m0 h dash upon h is equal to l upon f0. We have, sorry, where we have used the result tan beta equal to h upon f0 equal to h dash upon l, tan beta in this figure. Okay, so next one, here h dash is the size of the first image and the object size being h and fo being the focal length of the objective. The first image is formed near to the focal point of the eyepiece. The distance is l. The distance between the second focal point of the objective and the first focal point of the eyepiece, focal length fe, is called the tube length of the compound microscope. The next, at the first inverted image of the near the focal point of the eyepiece is, sorry, we have used the result of the discussion above. The simple microscope to obtain the angular magnification ME. M is due to it when the final image is formed at the near point is ME is equal to 1 plus D upon FE. That's the formula. When the final image is formed at infinity, the angular magnification due to the eyepiece M0 ME equal to D upon FE. The total magnification according to the equation 9.33. So image is formed at infinity. M equal to M0 ME equal to L upon F0 multiply D upon Fe. Clearly, to achieve a large magnification of the small object, hence the name microscope, objective and eyepiece should have a small focal length. In practice, it is difficult to make the focal length and much smaller than 1 centimeter. A large lenses are required to make a large L large. For example, with an objective with f0 equal to 1 centimeter and eyepiece with focal length f equal to 2 centimeter and tube length of 20 centimeter, the magnification is m0 me. L upon f0 multiply d upon f0 will equal to, we have to put the value and find the solution 250. Various other factors such as the illuminations of the object contribute to the equal quality and visibility to the image. In modern telescope, microscope, multi-compound lenses lenses are used for the both objective and the eyepiece to improve image quality by minimizing the various optical uh, aberrations in lenses. So this is the presentation area of this chapters, and the rest left of the subtopic will uh, completed by me tomorrow. Thank you for watching.